Well, hello friends. Today we are going to do some performance work. We are going to profile the HTTP implementation and then try to do some optimization based on things that we find. So we have this page here, the Happy Birthday webpage. It's a copy I have running on my host machine. And as you can see while we're loading this page, we're using a lot of CPU up here. It just spikes like crazy. And if we look in the system monitor, we can see that the protocol server is, or was, basically the main offender. Protocol server and network task working together. So network task is the kernel side of the networking code. Like whenever we're receiving data from the network, then it will be handled by network task. And then protocol server is the HTTP protocol implementation that runs in user space. And we can see here that it's running in user space quite much when we are doing some downloading. So I think what we're going to do is we're going to start with a clean slate, and then we're going to get a profile of protocol server when it's running at full steam. And then we will use the new profile viewer to look at what's going on and then try to optimize whatever's going on so that we can do maybe less of it or more efficiently or something. So now we have protocol server here. It's PID 17, so we'll be ready to profile PID 17 once it gets churning. So we'll just let it get started, and now it's running at full CPU. Get some samples, and we'll stop there, I think. Don't need too many samples, but some. Okay, now we have proc profile, and we'll just save this in protocol server.prof. And then we can open this in the profile viewer. Okay. So let's see. This is doing a little bit of GUI work here in the profiler. Just fixing up the look of the tree view and everything. So most of the time we are spending in, or the vast majority of the time is in socket receive. And then we also have some time in HTTP job finish up. And that actually appears to be all in byte buffer deallocation, which calls to free, which calls to M1 map. So this whole thing here ends up in the kernel, basically. Actually, maybe it would be interesting to show kernel stack frames in a different color, but well, should just remember that for later. Might be interesting. So what are we doing here, though? This is the majority of the time. So down here we have a split between a syscall to the read syscall, which is the majority of the time. And then we have a minority, but a chunky one, in byte buffer creation, so malloc basically, which is called mmap, which will do some pretty heavy work, just allocating memory regions. And I think at some point here, interrupts get disabled, so we don't really see what it's doing. But it's mmap, allocating new memory. But the read syscall is the biggest one. So let's go here. Socket read, IPv4 socket receive from, and the majority of the time is spent in the destructor of a kbuffer impl, or destructor of a ref pointer to kbuffer impl, but that's a very thin thing. It will just call kbuffer impls destructor, which is this class right here, and it doesn't have a destructor, so it's just default, which means that it will just invoke the destructor of this, which will be the destructor of region, which will disable interrupts, which is why we don't see any more info here. I mean, we see this guy right here. But basically, all the samples that we get, they get stuck here. Like, it looks like this is where we are, but this is a very small function. I can show you in the assembly, but we just don't see more because interrupts are disabled, so we're unable to sample with the profiler. But just for clarity, I'll show you what this function looks like in the kernel. So null ref footer to kbuffer impl. Oh, it's here. Oof. Oh, can we get it like this? So actually, it's not super tiny, but it is. This is the non-null ref footer destructor. So what that will do is, where's the destructor? Here. Oh, right, this is why it's heavy. Or it's not the whole reason, but we'll dereference the pointer as long as it's not null, assign null to ourselves, and then replace it with this bit pattern. This is not the heavy thing, but let's see, it will call operator delete in deref. So anyway, the important thing here is to know that the kbuffer gets deleted, so we call the region destructor. Now, region destructor is very heavy, and I think what we're going to do today is not optimize away the region destructor, but rather we're going to look at why is IPv4 socket, why does it keep destroying these kbuffers? Because a kbuffer is a memory allocation in the kernel that's in increments of the page size. So it's basically a page allocation. So we'll look in IPv4 socket, and oh shit, I should maybe have kept that profile open. Okay, so oops, that's not the branch I wanted. Here. This is where we want to be. So receive from IPv4 socket receive from. What will he do to clear an optional? I think we'll be taking a packet somewhere. Where is it? Packet. Here. We're taking a packet from the receive queue. Take first. And packet, I think, is the optional kbuffer. Oh, no, receive packet. But here it is. So I bet this is the destructor that we are running. So the received packet is whenever we're calling receive from on an IPv4 socket, we check if there is a packet in the packet queue, and we take that packet and give it to you. But I think in the case of a TCP socket, if it's a streaming socket, then we don't want to go packet by packet. We just want to give you as many bytes as you're asking for, basically. And I think this is a flaw in our socket implementation in the kernel, that right now we're always buffering packets and giving you one packet at a time, whereas we should really, in the case of a TCP socket, which this is because it's HTTP, we should just buffer the bytes and give you as many bytes as you can handle. So let's try to do that instead. So how should this work? Because we need the we still need the packet version per packet thingy for UDP. Because if you want a datagram socket, then we have to give you a packet at a time. So I think we're going to have two separate behaviors here. And maybe this comes down to how we handle incoming packets. So where's the receive queue? Where do we add to this? It's when we get called to did receive, which is called by network task, which is the kernel thread that runs whenever there's an incoming Ethernet packet or any network packet. Then network task wakes up and looks at the packet, figures out which socket is this for, and looks at all the sockets in the system and just routes it to the right process so that it can be picked up there. But I think we want to have a slightly two separate behaviors, basically. Like we want to have a streaming socket and a datagram socket. Or what do we want to call this? buffer bytes or buffer packets maybe, or like buffering mode. We'll have a buffering mode thing. So enum class buffering mode, or maybe buffering mode is okay. Or buffer mode. And we'll have packets and bytes. And you gotta be in one of these modes, so buffer mode. Okay, and I think we'll only let subclasses called set buffer mode. Okay, let's see, mode, and we'll just store this down here. Buffer mode packets. Packet. Oh no, packets, okay. All right, and then in TCP socket, we'll just override this. I think it's possible to make a TCP socket. On some systems, you can make a TCP socket that that goes packet by packet with some flag, but I'm not too familiar with that. That's maybe something we can deal with in the future. But actually, maybe we don't need to do this in the subclass. Maybe we can just do this in the, cannot have that at all, and then we can look in the IPv4 socket constructor, because here we're looking at the type. So we're saying sock stream, do this, sock datagram, do that. And wait, what does this do? TCP socket calls IPv4 socket sock stream. Okay, so we'll just look at socket type here. I think that'll be fine. So m buffer mode type sock stream, if so, buffer mode bytes. Otherwise, buffer mode packets. Okay, so now we can look at did receive, and this receive queue is not going to cut it if we are a byte buffering socket. So in that case, what we want instead is, I guess, just like a really big buffer to put stuff in. So we'll have like an optional K buffer. Byte buffer, bytes buffer, something like that. Receive buffer. So really you only need one of these, but right now I guess we'll have both for now, but in the future maybe we can cut that down. So let's see. So this is how we reject packets at the moment. We just, if we go over 200 packets in the queue, then we'll say, now you got a little too many here. Also, this will walk the entire linked list every time we get a packet to see if we have too many packets. It's not a very beautiful algo. Takes me maybe track the number of packets so we don't have to walk the entire packet queue to count them. Okay. So if buffer mode is buffer mode bytes, then the receive buffer, we're going to need in some kind of index into that thing. Maybe it can just be like this. It's pretty simple. So let's see. We can see if it fits. So I'll take that up there. We'll say m receive buffer if packet size is less than or equal to space in receive buffer. No, if it's greater than that, then we'll say we'll do this thing. So we'll say buffer is full. Okay. So IST space in receive buffer is receive buffer dot size. Minus the receive buffer index. That's how much space we have. Okay. And then memcopy. Wait, hold on. We need to store more information about this. Or do we? Maybe we don't. How does that work? Because I'm thinking, like, whenever you receive a packet, then what is the data that we store? We have the source address and the source port. And in the case of a TCP socket, then it doesn't matter because we've already stored this one, so we can just keep reusing it. In a datagram socket, it's different, right? Because you have to look at the source port every time. Because it's not a persistent stateful connection, so it's a bit different. But I think in the case of this byte buffering mode, then for those sockets we don't have to care about the source address and source port, so we can just memcopy the packet and then forget about it. So what we'll do is memcopy it to where exactly? Receive buffer dot value dot data plus receive buffer index. And what are we going to copy there? We're going to copy the packet dot data. And how much is it? Packet size. And then we increase the receive buffer index by the packet size. And return true. Okay, we have received bytes, and let's log this. Bytes in buffer is receive buffer index. Okay, that's cool. And then whenever we want to use the receive queue, which I guess we do in a couple of places, or is all of this in receive from? Everything is in either in receive from or did receive, so that's great. It's only used in those two places. So now we just have to update this place as well. So we'll say here, maybe we'll break this into two separate functions. But wait, hold on, we forgot something. In did receive, we have to update these two things. So bytes received needs to be updated, and can read. I think we'll put these up here as well, and maybe we can do it a little bit differently. Like that. So we can do this, this, this. And then we can do the logging down here. Can read is now true, and buffer mode bytes. Something like that. And maybe we'll just turn that on for now. But I think, yeah, we don't need the profile to keep working on this, so we'll just push forward here. And now we just need to make use of this information, because right now TCP sockets are broken now because we'll buffer bytes, but we won't let you read them. So we can actually see what happens is that we should crash, right, and did receive. Because, where are we exactly? Packet value. It's asserting. And receive, oh shit, yeah, right, because we didn't allocate the receive buffer. So let's make a buffer. I think maybe we'll do that. That's the first thing that we do over here. Okay. Then if and buffer mode is buffer mode bytes. Create with size. So how much do we want to allocate for receive buffer here? How about 128 kilobytes? How about 64 kilobytes? I don't have to go crazy. And then what are we going to do with that? Well, all of the interesting stuff is going to be in receive from, so that's where we should be going. I'm thinking, should we break this up into a separate function? But maybe that's not necessary. I'm not sure. We'll see. So maybe we'll do, we can do a separate function that we call from receive from. So IPv4 socket receive turn on receive impl. And we can have a U8 buffer, XD, buffer size, and what do we want to put there more? We have received packet. We want to put the peer port and peer address. So IPv4 address, peer address, U16 port, something like that. If we can populate it like this, because then let's see if buffer mode is so the old way of doing things. Receive packet. Maybe we'll do it. Maybe we'll do it separately. Okay, and then we'll have packet. We'll do that. And we can also have receive bytes, which doesn't care about these things. Receive bytes. Okay, and then right here we'll just do peer address U16, peer port, receive impl. Buffer length, peer address, peer port. Shit, we need to pass down the file description as well, I think. Yeah. Okay, so we'll pass that. Also, I don't know why this is cast into void here, because we end up using it. But anyway, we'll need to pass this guy. So we'll just do that. Okay, now let's put these in the header so that we can use them. Okay, there we go. What's wrong with you? Oh. All right. Description. So you want to come out of this with some packet data. An IPv4 packet. Oh shit, we shouldn't be giving it the user space output buffer here, I think, or rather just a buffer to put an IPv4 packet into. Although, well, we don't care about that, because on the DCP side, we shouldn't be buffering packets. Maybe that's a mistake that we're making. So did receive. Right now this is buffering bytes, but we are just putting the raw packets into this byte buffer. We need to do more processing here, now that I think about it, because we gotta strip off the IP headers and stuff. So let's see. Maybe this is a bit simpler actually than I thought, because if we know that in byte buffering mode we just have bytes or we don't have bytes, and then we can just block, get some bytes, and then we have the bytes. So all of this stuff right here is receive packet stuff, and what do we do with this packet? Now I'm kind of feeling like maybe we should leave this alone and we should have a short fast path instead, or like a short circuit for byte buffering sockets. So let's backtrack, because there's a much easier way to do this. So let's get rid of that. Get rid of that, and can say receive bytes, or what do we want this signature to be? Well, we don't need that in a separate function even. So let's do this in a much simpler way. So when we receive an incoming packet on the socket, then we have to treat it this way. Doof. And what are we doing in protocol receive? So should we go to protocol receive right away and then write it out? I think this is what we should be doing. Okay. This is getting a bit messy, but okay. Basically, here, if buffer mode is buffer mode bytes, then we lock if m receive buffer index is 0. Then, if the protocol is disconnected, return e and end of file. If the description is not blocking, return e again. Write run. And then, if receive buffer index, we know that it's not empty. Wait, why is this written this way? If it's empty, then if it's not empty, we know that it's not empty at this point. So receive buffer index, not blocking. Oh, wait, hold on. I'm about to make a mistake there. I thought we were returning always in this block, but we don't. I thought it was like this. So, let's not be silly. Now, so say that we have a packet, or if we don't have a packet, we want a block. So what we're doing right here, this is like this. Okay, so okay, we'll block, and by the time that we oh, excuse me. By the time that we get here, now we have a packet. So we should always have a packet when we are here, which means that assert m receive buffer index should be non-null, non-zero. And then we can just copy out the bytes. So how do we do that? We just say memcopy buffer oops memcopy to the buffer from the receive buffer dot value dot data. Actually, we have a data structure for this. Why am I not using it? We have the double buffer. We can just use that. Then we don't need the index. Receive buffer is empty. Just call read buffer length. And what do I have to cast this? And then finally, we will just return. We can even just return that. Okay, so we can return this casted to an int, and we're good. No? You don't like? You're expecting this to be an int as well? Ugh. Well, whatever. Okay. Okay, so now we just got to make sure that we put stuff into that buffer correctly. But then the rest is going to be okay. And the important thing to put things into that buffer is, I guess we should do this actually for the statistics. So right here, we'll do something like this. And received. Okay. And then now we just want to make it call the protocol receive whenever we are receiving bytes in the did receive. So here, instead of this thing that we were doing, we'll just do mReceive buffer write packet size. Okay, here we go. And packet and receive buffer is the receive buffer. Dot bytes and write buffer. That's pretty smart. How much space do we have? No, wait, this isn't how much space we have there, it's how much is in there right now. So what's the capacity of this thing? How do we know that? I guess we just decided for ourselves. So this is a little bit weird, but let's do it this way for now. We'll say goes up to 64K minus however much is in there right now. Okay, we'll do it this way, and then we can say size t here. Okay, and then we gotta call the protocol receiver. So protocol receive packet. Oh shit, yeah, because we shouldn't do this here. That's the problem. We should not do this here. This should be in the protocol receive. So protocol receive or do packet, and the output location is going to be the, well, maybe we have to manage this ourselves. Shit, this is going to be a bit weirdly factored, but, or, no. I don't like this. Because protocol receive expects us to give it just somewhere to put it, basically. Somewhere to put the thing that we're reading. Maybe we can just make a temporary buffer. Temp buffer. I don't know. We'll make it one page. It's kind of gross, but no flags, and say something like that. And received. And we'll get whatever we got from the buffer. Okay. And let's just hope that the packets are smaller. They should always be smaller than this. Although sometimes they, let's just start because we're not talking about Ethernet frames here. We're talking about TCP packets. Or I guess actually we are talking about IPv4 packets here. Which could be bigger. What's the maximum size? Right, 65,536 or 5. Just put this jackass on the stack. If we do it this way, then we're always good. Okay, let's do it that way. And received. Oh, goodness. And receive buffer. And receive buffer index. What do we want in there now instead? And receive buffer is a double buffer. We know how many bytes we have in the write buffer. I guess that's the thing that we can show. A double buffer in the kernel is a two-headed snake dragon buffer where you have, let's just see, you have two buffers, one for incoming data and another buffer that's being read. And then you always have a buffer that you can write incoming data into because it's not the same buffer that whoever is reading from the buffer is using. And then whenever you finish reading from the buffer, you swap them so that the buffer that was taking all the incoming data becomes the new buffer that you're reading from. So this didn't really work out. I'm guessing that we did something goofy here, bytes and buffer, blah, blah, blah. Seems like we got some good stuff happening here, but then we went up to 8K, and then what? Total received this much. Right. What happened? I'm guessing that we didn't do the packet boundary correctly somehow. Can read. Wait, does M receive buffer? We should probably do something like, we should check is empty. Wait, how does this work? When you write to it, then it computes the emptiness. And if it's empty or not, that's what determines if we should be able to read from it. So we'll do this. And there's always true. Because if we have some 0 length packet, then it shouldn't change the readability of the socket, I think. And this is actually interesting. Like, should we track the number of total packet bytes received or the total number of payload bytes received? I'm not sure what's the best. Maybe the total packet size. Anyway. So what we call did receive, if we are in byte receiving mode, let's assume that this stuff is working right. I mean, we could even dump out the stuff that we received. It's not terribly interesting. We know that the first packet is good. Probably the second one was bad. So how did we mess that up? This returns something. Do we need that? Probably we don't. I bet we're just messing up reading from this buffer. If the receive buffer is empty, say receive buffer is empty. Empty, yay. See how we fare here. Just to verify that we are taking the expected path. Oh shit. I guess there's some stuff happening. Now things got really verbose all of a sudden. Shit. This is not entirely trustworthy. Wonder why that is. Just a smoke test here to see if we are screwing ourselves with this huge buffer for some reason. Could that have been it? Load failed, so it's not working just right. Maybe we should have a temporary side buffer for this. We'll just say, we'll make a scratch buffer. Scratch buffer value data. Let's see. Okay, and then we will have if it's a sucks, or if this mode is buffer mode bytes, then scratch buffer is k buffer, create with size 64k. All right. So, what is going wrong? How do we figure this out? I guess we should have one big page rather than many pages like we're doing now. So What's the thing? Why would we ever need to go packet by packet? I was just thinking about things. I guess we do have this load right here. Oh, no, that's not the place where I want to go, actually. I want to go to serenityos.org. Ploop. It's a simple load, and then this one is a bit more complicated, but it's only this separate resource, and it messes up. And then I guess we disconnect the socket before it's finished. So why does that happen? We're gonna need some more info. I haven't looked at the TCP code in quite a while, so this is a good refresher. Alright, so now that worked. Let's do it again. Hope that it doesn't work. Stop working. Okay, thank you. So, what happened here? We're fetching the data, blah, blah, blah. Buffer is empty. And then that's when we determine that we have all the data. Right. So there's nothing in the receive buffer. Maybe we've just disconnected. These messages don't sound very good. Should probably look at what's up with that. It's curious that we get these smaller packets here. I guess this is the HTML, or is it? I would assume that this is the PNG. Maybe this is HTTP headers or something. When it comes to data. But it's curious that we get 4 kilobytes, 4 kilobytes, 4 kilobytes, 4 kilobytes. So are we doing something differently than we should be? Let's see. Buffer mode bytes. The receive buffer is empty. So if we're disconnected, we will, I'll say EOF. So we can log that here. That's fine. Non-blocking socket, returning E again. And then here we're gonna block until we have some stuff. Blocking until we have something. Blocked over can read is m can read. Okay. Make and sync and run. So what is happening? I feel like there's probably something that we were doing in the packet buffer by packet path that we're not doing here now. Like that very last packet after all the 4K ones, I'm expecting this one. And I feel like that one didn't always show up. So what's up with that? Well, now it's just gonna work. All right. Okay. Non-blocking socket returning E again. So receive buffer is empty. So why are we here if the receive buffer is empty? Is it that we are not updating the can read flag after we read, perhaps? So maybe we call again too soon, and then we discover that, hey, you told me I could read, but there's nothing here. And we think that means end of file. So probably what we should be doing is updating the can read flag after we do read. And this would be mreceive buffer is empty. Something like that. I feel like maybe that's the whole trick. So now, did we load everything? No, we didn't. Oh, no, no, no. Look at this. Oof. Holy moly. Alright. That went really wrong. Oh, wait, hold on. Shit. It should be is non-empty. We can't read if it's empty. Although the amount of weirdness that that caused was alarming, but... so we go here, and what if we load some page with all the PNGs? Look at them go. Okay. It successfully loaded everything. So, shit, I think that we have actually done it correctly now. So let's turn off all of this pesky debugging code so that we don't have to stare at it. Where was that one that we had? Did receive. And same in TCP socket. Let's turn that off. And it's still so noisy. Yay. I still have all those messages with the yay and the nay. So let's get rid of those as well. And once we can confirm that this is working, then we can make a new profile and see how it fares when compared to the old one. Of course, the old one is gone because I keep overwriting the file system, but we remember what it was doing, right? So, here we go. I feel like that was pretty fast compared to the old one. We didn't have that prolonged CPU usage period there. Maybe we can even profile this. So let's try to... This is a bit alarming. The fusing packet. Since the buffer is full. Packet size is greater than the space in the receive buffer. Let's assert that it's possible to read at this point. Because if it... I'm curious, like, is it the case that somebody's not draining the receive buffer? Shit. Well, we're getting everything. So what is up with this? I'm not sure. Are we maybe not killing the connection correctly now? Right. So what happens in receive from? I just want to look at what we did on the packet by packet path. Well, it is working, so it's probably we have something to clean up somewhere, but let's not worry too much about that right now because it's not like the sockets are perfect anyway. I think the general idea here is good, so let's kick up a browser, and we don't need that one. PS grep protocol. Now we're gonna profile this guy again. On. And oh, what's happening now? Network task. Okay, I think this is a bug that happens sometimes. I'm not sure why. Some network task just gets hung. So let's overlook that one and try one more time. Okay, boop, boop. Oh, there we go. And we'll turn off the profile here. I wonder if we can capture the whole thing. It's pretty cool because I know before we couldn't even capture the whole load in a profile because it would run out of kernel memory. So this is our new profile. Our heaviest stack is now HTTP job finish up. Here's the socket receive, which we have successfully reduced to a minority stack frame. Look at that. Most of his time is now spent in allocating buffers instead of the quite minuscule time spent in the reads syscall. That's freaking cool. Look how little time is spent here. All of that because we stopped queuing up packets for TCP sockets, and instead we just save the bytes and throw away the packet. And I bet you that we can do way, way more to make this even faster, but that might have to do, we might have to do that in the kernel because I think the kernel is being very inefficient, doing like a separate VM allocation for every packet, incoming packet and stuff like that. And we could do a lot of work to make this a lot better. But what's happening here then? So yeah, it's just a byte buffer clearing. Maybe we can look at that too, but let's see. So net, I think maybe we'll just be happy with this and not think much more about it. And I'm sure that we'll butt heads with this, or we'll come back to this again anyway. So IPv4. Let's use byte, or no, buffer. Only buffer payload bytes for stream sockets. Since stream sockets don't actually need to deliver packet by packet, packets at a time data and receive from, they can just buffer the payload bytes instead. This avoids having to deallocate. This avoids keeping huge numbers of key buffers per incoming packet in the receive queue, which was a big performance issue in protocol server. This code is definitely not perfect and something we should keep improving over time. So here in the HTTP job finish up, that's in an HTTP job, we have a vector of byte buffers. These are incoming data buffers. And whenever we receive data, then we put it in one of these. And it's a little bit of a strange strategy for buffering. I'm thinking we could probably do this differently, because I'll show you what this actually looks like when we're using it. So we get the payload, which is like an incoming data payload from the HTTP implementation. Let's see, how do we get that? We get on ready to read, and then we payload socket receive. Right. So I'm thinking here, this is a call like this, socket receive. We could do something slightly differently here, where we use something more like this. Wait, this just calls the byte buffer read version. Okay, so we could do something a bit sneakier with not creating a temporary byte buffer, but instead getting do a direct read from file descriptor into some memory that we pre-allocate. Is sort of what I'm thinking. Not exactly sure. But because right now we have a byte buffer per packet that we get, and that's not super efficient. We need some kind of data structure here that is better at growing than allocating these things one at a time. So we could use bigger buffers, because I think the problem is mmap, basically, and munmap is heavy. So we could make them less heavy, but I don't want to work on the VM system right now, so let's just do less of this. Because here, finish up. This is the thing that we were seeing. This guy right here is the costly one, because it will clear the, all these byte buffers, which will turn around and call clear here, which will free the data, which is a byte allocation. So why is munmap slow, by the way? It's slow because of many things. We have to find the memory region that we want to unmap. Then we call deallocate region, and there's, like, in the region code, there's all of this stuff, like, because regions are stored in arrays, and that's not super great. Although this makes me realize that I guess we could, at least we could sort them, which would allow us to use binary search, but I would kind of like to use some kind of tree for the regions instead. I wonder if they are sorted already. I think they're not. You could imagine just sorting them after an unmap, but then we always have to resort. We should put them in a tree, but I don't want to do that right now because it's a big refactor. But someday we should do that. Because the thing is, when you have a process with like hundreds or thousands of memory regions, then you're constantly scanning through this long ass O of n vector of regions, just looking for your region, and that's super not efficient, and we're doing so much of it. So we definitely want to switch that over to something that's like O log n instead. Whether we do something like a red black tree or some kind of a hash table thing, I don't know. But not right now. Okay, so let's create ourselves some slack here. So maybe instead of taking the buffers that we get verbatim, we will have a system, because there's no requirement that these have to be like each packet as we got it. So we could definitely, wait, why were we getting exactly 4 kilobytes anyway? We were asking for 4 kilobytes at a time. We're asking for page size. What if we just increase this? What if we just say, like, hit me with 64K, because I don't care. And, oh shit, we gotta recompile. Let's do everything. Because if we only ask for 4K, then that's the max we're gonna get. But if we ask for 64K, we might get 4K, we might get 64K, we can just get whatever he has available for us, and that would create a lot less buffers. Because I was thinking we could like make one big VM allocation and write into that, but I think maybe we can sidestep a lot of our problems just by increasing this buffer size here. So let's get a browser, yes, profile, protocol server 17, profiler bro. And the last one is not going to finish, really? One pending resource. What's not finished? This is a bit weird. Oh, I guess it's the very first picture. Sketchy. So profile. Oh, we can't do that yet. Okay, so finish up. We're still spending most of the time here, but presumably less of it. This is a bit alarming. I wonder if I did break something. How big are these anyway? I have them on my local machine here, so we can actually look. Oh. can receive a megabyte at a time. We don't care. Oh, let's rebuild. I'm just thinking, like, what do we say? We don't care if we get a megabyte, right? It's just a max that we're willing to take. How does this work in practice, actually? Read. Well, we make an uninitialized byte buffer to hold this, right? Which will just make an mmap allocation internally. Bloop. Okay, I don't like this thing that happens sometimes where it doesn't start downloading at all. But this is definitely better performing than we had before, so let's get a profile of it. Also, all of that header spam. Oh shit, we ran out of memory in the kernel. Why is that? Why did we run out of memory in the kernel? Have we introduced a leak on JS? How did we introduce a leak? Okay, buffer. IPv4 socket. We made that scratch buffer, and we have the receive buffer. The receive buffer uses vectors internally, but this was this is actually using kmalloc. This was a page table allocation. Oh, I guess because we're allocating, you're just making more and more page tables all the time because of that 1 megabyte. We're just soaking up the address space. Alright, maybe this was not a terrible idea. So we'll just say. But I don't love that strategy. We can do better. We can do so much better. So socket receive. We can do a big allocation. These don't have to be they don't have to be byte buffer create. We can also use byte buffer wrappers, which are non-allocating ones, and then we can manage our own memory. I think maybe we'll try to do that. Because what happens in byte buffer right now, where create uninitialized, we'll call byte buffer impl, which we'll call kmalloc, which we'll call malloc, and we'll get a huge mallocation. It will be a big allocation block. So I think we can do better. Yeah, we can definitely do better. I don't know why I keep saying that to myself. But how are we going to do it? We'll have a size t m index into last received buffer. Okay, so whenever we are receiving data, So we'll just do it this way. Read from file descriptor into buffer, size of buffer. This is really gonna mess up the socket though. Shit. Oh, this is so frustrating. Like, the design here is the fact that we are using byte buffers for everything makes it very annoying to deal with them because they always use malloc. Okay. I'm just not. I'm gonna scale back and calm down, and we're gonna say that this is 409. So page size was too small, right? So we'll just say 64 kilobytes. And we'll let it go for now. Sometimes you gotta let it go. We'll come back for you, but right now we're just going to increase the thingy a little bit. So, what was this? It was libcore. HTTP job receive buffer size from 4K to maybe to 64 KB. 4 KB gets pretty mmap heavy for when downloading larger files. So I'll bump this a bit to reduce. This is called pressure, or VM pressure, or just pressure. To reduce time spent. Memory allocation. Yeah. We should put a little thing here. This can be improved in various ways, but I'm not sure what the best way forward is at the moment. Not exactly sure, so I don't wanna get stuck here. So what else was going on while we were loading though? Could we profile some other aspect? Let's do one of those loads again and see. So now we can see the network task is running. Maybe we can try to profile it, see if it's possible. It's a little bit trickier because it runs in the kernel, but it might still work. Network task, PID5, so see how this goes. If we just bring this up and say, oh, here we, oh shit. Can I profile it now? Aha. You can't stop me. Did you just stop me? Crap. Okay, well, I think maybe that was just a fluke. Damn it. Alright, come here, you. Okay, I'm stopping there. It's very possible to run out of things, run out of memory when you're doing a profile. So, cat proc profile network task profile. Wait, what's happening? Okay. Oh. The machine is totally bogged down by the network task, I guess. So what is it doing when this is happening? I want to see it. Send TCP packet. We are just sending TCP packet over and over and over. That doesn't sound right. So we definitely have some kind of a bug where we are calling this over and over. Do we get stuck in a loop here somehow? Who's calling this? So many places, I guess. It's a bit unfortunate here that we can't see where exactly in the function the call was. But it really gets caught up there. Still though, I feel like this is like a buggy thing, like something bugs out and then we get that bad behavior, but I'm more interested in like the not bugged out behavior. So profile 5 on. Can we just get a normal run, please? Just succeed? Yeah, this is more of a successful run. Okay, so get proc profile. Okay, now showing the normal run. Okay, now we're talking. So this is what network task is busy with in a normal run. Send TCP packet, lots of this, of course. E1000 network adapters, send raw. Very heavy apparently. Oh, I bet it's because of this. We're just busy waiting until the packet is sent. We could probably do better with that. Jeez, that's heavy. Busy wait. I totally forgot that that was done that way. So let's try to not busy wait and see if we can avoid that. And then what else do we have? More K-buffer clearing. So same issue as in the protocol server, just throwing away the receive packet queue. I guess here we are receiving packets in K-buffers and then freeing them is expensive. So just more of the same. Did receive double buffer write. It's pretty heavy, but I mean, that's okay. So much better than what we were doing before, I think. K-buffer copy. Well, anyway, the absolutely heaviest thing seems to be the sending the raw packet out, which I bet you it's this right here, which is because we are telling the network card that, hey, there's a new packet waiting for you to transmit, and then we wait like this for the network card to say that it sent the packet. So what we should do here instead is we should make a wait queue, and then we can just use that to go to sleep and then wake up when it's been sent. And I feel like we should get an IRQ when that happens. Are we not getting that? Switch over to kernel mode. All right. We have handle IRQ. God damn it, I forget what everything is in this card. I think we can get an IRQ when we should be able to get an IRQ when something has been transmitted. Let's look it up. Status, what's it called? Maybe it's up here somewhere. What were we doing in handle IRQ anyway? So I guess if status is hex80, then we receive. So presumably there's some other status that that means that we transmitted. Oh, maybe these guys have the info that we're looking for. Where do they handle the IRQ? Oh, this looks familiar. Okay, well, let's just assume that we get an IRQ for transmitting. And we'll see what that looks like. So maybe we can print out here. But we can do even like this. M wait Q. Like all. And then in where's this guy? Right here. Do this in any more places? No, it's only here. Okay. I think this is not going to be good enough. It's going to cause us to wake up from receiving packets as well. I just want to see if the basic mechanism would work. So current wait on M wait Q. Maybe we can do something like this. Otherwise, we'll wait again. Then we'll just check after every IRQ. Thread. We're not waking up, are we? Okay, so now if you look in PS, we should see that network task is queued and protocol server is queued. That means it's queued in the kernel waiting for something to wake it up. But nobody's waking it up. Okay, so how do we find this? Intel i217 IRQ. Datasheet. Here we go. Can we get something more than just a datasheet, maybe? Problem loading page. Don't be this way, you guys. Okay, thank you. So what can we find in here? Programming interface. Programmer visible state. Do we have C0 somewhere? Is this actually the card I was looking for? I feel like it was. Packets are ready for transmission. Blah, blah, blah. Actually, I guess we can see what we think the card is. Network controller, it's one of these, 82540EM. sure that we have the right thing. All right. No. Oh, maybe you can't search here. No, you can. Okay. Anyway, blah, blah, blah. Interrupt signal. Yes, yes, yes. And this is very hardware oriented. I was hoping for some programming information. Commands. Let's see what we can find. Dun, dun. Still very hardware oriented. This is very suit and tie. Programming. Oh, I guess we can maybe read about it here. And maybe these guys have some information. Da, 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 da. No, not the export specification. I don't care about that. Data sheet. Ugh, why are you this way? Okay, what do these guys say? Do they have any links? Thank you. Okay. So transmit. We want to see. Can we get some interrupt mask up in here? No. Is it possible to find anything? Yeah, it searches. Okay, fine. So, blah, 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 blah. Terribly fascinating, and so on. Packet reception. That's not what I want to do. Packet transmission. That's what I want to do. Okay, so we received a block of data to transmit. Protocol stack calculates the number of packets. Yeah, sure. Transmit data storage. Stored in buffers pointed by the descriptors. Sounds about right. And this is the maximum packet size. Sure. Transmit descriptors. Sure. And then there's status bit, I think. STA status field, right. Report packet sent. It's reserved and should be blah, blah, blah. Wait, what does that mean, report packet sent? That sounds like what I want. When set, defers writing the DD bit in the status byte until the packet has been sent. So it's if you want to be sure that the packet has been sent, not just loaded into the transmit FIFO. Sure. But how do I get an IRQ? I want to get an IRQ. So If an interrupt condition, whenever a transmit queue goes empty. Yeah. So I guess I'm masking the interrupts somehow. Mask, interrupt, imask, right. So what is the imask? Interrupt mask. And how are we doing that? iMask is D0, so that's interrupt mask set read. Okay, so interrupt is enabled if its corresponding mask bit is set to 1 binary. Sure. So we want to make sure that we have a 1. And here are the different interrupts we can enable. Transmit queue empty. Wait, so iMask. I don't know what this is. FF and not 4. And not 4? We're turning off the link status change interrupt. But all the other interrupts up to this point seem to be enabled, and then all of these are disabled. So I would think that we would get transmit descriptor written back, transmit queue empty. We should get something here. Handle IRQ. Reg iMask 1. Wait, what is... Oh, wait, hold on. If you want to disable an interrupt, you have to write to the interrupt mask clear. So here's that. Interrupt mask clear. D8. Are we ever writing to that? We're never disabling interrupts. Okay. Send raw. Okay, I'm just gonna see if this ever wakes up. Wake up. It just never wakes up. Are interrupts ever disabled? Enable IRQ. Wait on the queue. Wait, hold on. Are we assert interrupts? I mean, obviously they're enabled, or the whole system would hang. So why don't we get an IRQ? Handle IRQ. I'll just print this out because this should be happening fairly regularly, I would think. We got one right here. And then what? Try to wake everyone that was waiting for it, and is that not good enough? I mean, I guess we woke someone up here, but damn it. Descriptor status. So what actually happens? So until okay, what if we just do like a sloppy version of this? So like, wait, hold on. Am I just doing something really dumb? Oh no. Oh, I have the condition reversed. Although, I feel like that's not the problem because it still wasn't woken up. So I never got wake up. But what if we just do a sloppy thing here where we do like scheduler yield. And then at least we just yield to other processes instead of hog the CPU while this is happening. Okay, and then I don't know exactly why how to get a transmit IRQ at the moment. We'll have to look into that at some point, but this does seem somewhat promising. Let's see if this is actually a improvement if we profile the protocol server. So browser, profile, oh no, network task, sorry. Now we're doing network task. Loading all the resources and finished, and save the profile. Okay, now let's see it. We're still stuck here in send raw because we're yielding and then still not good, right? Because we'll just be woken up here again. So, damn it. What would be the right way, I wonder? Why doesn't it wake us up? I'm sorry, this is so weird. So how does this work in QEMU anyway? Let's see, hardware. Net E1000, I guess is the one we're using. So grep RQ. So E1000, let's look in that guy, RQ. So what is it that we are doing to him? We're setting his TX desk tail. TX, it's the transmit descriptor tail register. We're setting it to, it's a circular buffer, so we're setting it to, or ring buffer or whatever, setting it to the point to the current thing that we're trying to transmit. I guess they don't call it tail, they call it ring. TX xmit seg transmit segment, can that be it? What is this? Process TX descriptor. Okay, that sounds like what we are interested in. So how does that end up there? Start transmit. Why are we in start transmit? Because set to cuddle. Set to cuddle. So presumably, wait, who's calling that? Write ops. To cuddle. T cuddle. TX control 400. The cuddle register transmit enable. We always have it enabled? Interesting. Start transmit, set tcuddle. What's TDT? TDT is transmit descriptor tail. Ooh, that's us. 30, yeah, this is us, TDT. Okay, so they set the transmit descriptor tail. They seem to react to when you're setting that, and then they call set to cuddle. And set to cuddle calls start transmit. And then what do? They do a DMA read of whatever we're trying to transmit. And then they process it, and then what's set ICS? E1000 regs. Interrupt cause set. Ooh. Wait, what was the name of it? A C8. Okay, so C8. C8. I'm interested in that. Set start xmit. So they were setting it to cause. Cause is UN32, DXQE, I guess that's transmit Q empty is the interrupt cause. So when we get an IRQ here, what we do is we look at register C0. E1000 regs C0. What is that even? I don't know what's going on here. I feel like we should be looking at the cause register. But anyway, what we want to find out is why isn't there an interrupt to begin with? So cause txdesk process txdesk yeah, so on and blah blah blah, and then we do a transmit, and we know that we're sending something, so xmit sag. Or is it the case that sometimes we put some bogus packet that we don't send, but then the status would still become 0, so status, or do we have the STA bit? The script, okay, wait, hold on, it was updating some bit. Process txdesk dp xp, that's the context desk. Wait, what's one of those? I think this is the one that we're looking for. Status, this is the one. Fields.status. Okay, fields. Why does it become, because this thing seems to become 0 when we're using this. So is it all getting zeroed out or something? I guess write back is writing something back to the descriptor, and it's just overwriting. How does this work? Stat dd descriptor done 1. So it becomes 1, right? Presumably that's the bit that we are waiting for. Dot status, is that the bottom bit here? Actually, it's a bit weird. It's not a bit that I'm looking for. So Rx TX. Status CSS and special. That's this part, and then the other part is length, CSO, and CMD. Oh, I guess they just do it differently. So they have upper.data as some union way of accessing this. So upper.data, they overwrite this. Those jackasses. Oh, and this is actually the bottom part of it. So yeah, okay, so it is this thing. They are setting that to 1. But then why don't we get an IRQ? I don't get it. Where do we set interrupt cause? How do we know if we have pending ints? Set interrupt cause. It's really nice to be able to read this emulation of hardware if you want to figure out what's going on. It's a bit less cumbersome. Of course, you might end up implementing some emulator-specific behavior rather than the real hardware, but at the moment I don't really care, since I'm just developing in the emulator anyway. So we have PCI set IRQ. I'm guessing that that's where we actually trigger an IRQ here. So set interrupt cause is called by set ICS, and set ICS is called here start transmit, and we should always have this interrupt cause. That's what makes it so weird, that there should always be an interrupt. Unless TX is not enabled. But then we also should get stuck in that loop. Yield. It's volatile, yes. Maybe the thing is that we have to make sure that interrupts are disabled so that we don't get woken up too early here. maybe we get woken up right away. Because now I'm thinking, maybe writing to this thing synchronously in the emulator causes this to create an interrupt right away, and we get woken up right away, and we don't actually have a chance. So there's a race condition. Could that be it? So what if we just disable interrupts for a moment here? I'll just say disable IRQ. And then here we'll just enable IRQ. And current wait on and wait queue. Like that. Will that work? Oh, seems like that was it. Interesting. That's very interesting. Then, cool. Let's get a profile of it then. Man, went all over the place there just to realize that I had the race condition in my own code. So we'll profile network task on. Okay, and boom, boom. Cat proc profile. Still, all that time in Central. Why? I mean, is this just where we are all the time? Handle IRQ. Oh shit, yeah, right, because now we actually see that here. Oh, okay. So, did receive, it's right there. So the IRQ comes in, called did receive, and we get a page fault. Network adapter did receive. And the reason that we get a page fault is because we make a kbuffer copy. Right. So this is totally normal. Interesting. Create 0. Fascinating. So at least I think maybe we just sort of moved the problem a little bit here, because it's not significantly faster. We just removed one busy wait and turned it into a smarter wait, but I think that busy wait was always succeeding anyway immediately, because it appears that the E1000 driver in QEMU will synchronously give you an interrupt right away when you try to transmit something. That's why we did we had the race condition here, right? Because right when we do this, it will immediately it seems like it will immediately give us an IRQ. So we have to have IRQs disabled so that we can handle them ourselves when we want to. Otherwise, we've already been woken up by the time we get here. And we're not going to get a second IRQ to wake us up again. Right. Much humming. Also, this thing needs some locking. of some kind. But that's a different issue. So why is did receive so slow? This kbuffer thing, right? So we create a kbuffer of every incoming packet. And that's pretty expensive, I guess. I think we could probably do something smart with these. Like we could have recycle them somehow. Packet queue, kbuffer. That's the only way we interact with this is DQ packet, and then who calls that? Network task, DQ packet. Okay, and he puts it here. And then he takes that with him here. Packet maybe null. Comes a packet. Now he has a kbuffer. And he eventually gets rid of it. So, that's curious. Memory allocation on the kernel seems to be like the big performance problem in this operating system, honestly. Just look at this. It's all kbuffer clearing, kbuffer copying, this is kbuffer allocation, did receive. This is double buffer write. Okay, that one is okay, because this is just, we can be smarter, but this is just, I think it's just appending to a write buffer, which if we look into it, I bet it's going to be, yeah, it's probably grow capacity, actually. It's probably allocating capacity for the buffer. Everything is allocation. Fine. Well, can we do better with the, let's see, let's commit something first. So we made some changes here that I don't know what they were, so let's see. Let's just restore things to the way that they were. Because this one is really simple. We're just adding a wait queue that gets woken up whenever we get an IRQ. And then you can just put yourself on that thing if you want to wait for an interrupt. So we'll say E1000. Use a wait queue. A transmit IRQ. And then indent receive. I think we can dequeue packets differently somehow. We can dequeue it into a buffer. We can give you a copy, for example. And then we can just have a rotating set of kbuffers here. That would be one option. We could cache them. So this would be something like, let's see. Wait. I was thinking we could like give it back somehow from network task. DQ packet. So after we run here, packet, maybe no. So if we do have a packet, we could say, we have some scope thingy, scope guard. do something like this. So return packet guard scope guard. And we would say, oh, we don't know which adapter it came from, actually. So, oh shit, that's annoying. Okay, we don't know where it came from, so we gotta do this differently. But instead of having a K buffer, we could also just have a buffer. So U8 buffer, 64 kilobytes. And we'll just dequeue a packet into that buffer. If not dequeue packet into the buffer. Okay, otherwise there's a packet here. And what is the packet size? That's what will get returned to us, I guess. Packet size is dequeue packet buffer size of buffer. Okay, like this. If packet size is that, then that. Okay, and then packet size. Packet. This seems like it could actually work. So we'll make a copy, but it will be way less expensive than an allocation. Packet size. Packet size. Packet data. All right. Now this is going to return, what's the pending packets? Oh, that's the number of pending packets. This will return a size T. And for the adapter, we will try to dequeue a packet. Let's see. No, like this. This will take a buffer and the size of the buffer. So okay, and then buffer size. Cool. What's going on down here? What's this yellow? Oh. Okay, and then a network adapter. dequeue packet is going to be like this. Network adapter, and the trick is now we're going to keep these buffers around. So cached packet, unused packets, something like that, unused packet buffers. Okay, dequeue packet, U8 buffer, size D buffer size. And assert that it can fit. Or wait, hold on. If it's empty, we'll return nothing. Auto packet is m packet q take first. Less than or equal to packet dot size. Like that. Packet size. Oh, actually, it's size t. Packet size is packet dot size. And then we'll mem copy out to the buffer. Packet size. And finally, m unused packet buffers. Append. Packet. Maybe we should count how many of these we have. Unused packet buffers. Count. If we have less than 100, we'll keep it. Okay. And then when we want to add one, instead of always using kbuffer copy, here's where the magic comes in. So if m unused packet buffers is empty, see, buffer is, if it's not empty, or no, if it is empty, then buffer is kbuffer copy data length. That's fine. Otherwise, used buffer is in unused packet buffers. Take first. If it doesn't fit, so if it's less than length, then we'll just do this. It's not perfect, but it'll be okay. Oh no, wait, hold on. This is the one that's weird. 16. Okay. And then here we can just append the buffer, that value. But if it does fit, oh, so we should write this the other way around actually. So if length is less than that, then we can mem copy it in. So mem copy into buffer value data and length. Buffer value set size length. Wonder if I got all this right. What the heck? How am I causing this suddenly? I guess I'm casting this thing here to an Ethernet frame header, yeah. So packet is U8 at this point. Wait, what? I'm confused. So why am I not allowed to do this? Subscript 0 is above array bounds of this. I mean, I'm sure it is, but why? Ethernet frame header. Payload. I'm so confused. I don't know why I'm causing this warning. So 21. Where are we calling payload? Not anywhere that we're using, or not anywhere that we're changing, right? So am I just upsetting the compiler in a new, unexpected way somehow? I feel like I accidentally changed like a pointer to a value somewhere, and I'm not exactly sure where. So I guess we will just diagnostic. Let's just ignore this. So we can do something like this. Oh no, wait, not that one. This one. GCC. And where are you? Ethernet frame header. We will ignore array bounds. Maybe I'm doing something obviously wrong and I just don't see it, but I don't know what. Okay, so that's pretty good. Let's get a profile. Wait, what was the PID? 5, yeah. Okay, so what are we doing now? Still the same? Kbuffer copy, all of it in kbuffer copy. Shit. Why is that? I guess I didn't do the reuse correctly. Length is less than, what if it's equal to? Because if all the packets are the same size, and then actually here, let's say, reuse. Just to get a feel if it's happening. I don't see this message anywhere. Okay. Unused packet buffers. We should decrement the count at some point. Is that what's going wrong? We do it 100 times and then we stop doing it? Yeah, that was it. Okay. Cool. Okay, so now we are reusing our packet buffers, if possible. So let's get a profile of that. Ploop. Oh shit. I guess I ran it twice now. Maybe I screwed up the profile. No? Okay. Look at this. Super cheap. Okay. So did receive has now become way, way cheaper. You can see we're not spending nearly as much time in there. And how fast did it actually go? Both. Yeah, sometimes it doesn't work. Okay, why don't you work now? Okay. Yeah, I'll probably introduce some kind of bug here. Excuse me. Because now it's a bit flaky and now we crash on what? PNG decode. Well, at least that's not related to this. See, the amount of time we spend with extremely heavy CPU usage is way down. And there we crash. Why did we crash? Is PNG decoding again. So I'm guessing we get some data corruption in the download somehow. But I've seen this before many times, so it's not new. Anyways, I think the changes we're making generally today are pretty good, although I have to spend some more time on figuring out what is wrong with this before I actually push these changes. So I'm not going to be able to continue recording the video right now, so I'm just going to end it here. But I think we've been through some pretty interesting stuff today. So we're profiling, and then trying to optimize based on that. So what do we have so far? We have buffering bytes in the streaming sockets. Maybe that's where we have a bug. I need to look into that, but not right now. And we bumped the receive buffer size a little bit, and then we use a wait queue in the network card to sleep. And here we switch the network task to reusing the received packet buffers. Reuse. Try to reuse incoming packet buffers to avoid allocation churn. Majority of the time in network task was being spent getting and deallocating K buffers for each incoming packet. We'll now keep up to 100 buffers around and reuse them for new packets if the next incoming packet fits in an old. This is pretty naively implemented, but definitely cuts down on time spent in network task, or time spent here. Yeah. Okay, so I'm just gonna stop here for the day, I think. So I hope you saw something interesting, even though we didn't finish everything that we wanted. And I mean, we did some things, but it's a little unstable, so I don't want to push it just yet. But nevertheless, I'm very happy with Profiler so far, and I can tell that it's going to be a big help in moving forward and making the system a lot better, because we haven't been able to get this kind of information before, so this is really, really exciting. To get this capability suddenly. So yeah, thank you for hanging out, and well, maybe we can open it like this actually. Yeah, of course we can. So thank you for hanging out, and maybe this is something I should optimize next, a debug statement. And I hope your projects are going well, all of those things. Thanks for hanging out. I don't know what to say. I'll see you next time.